Hi everyone, good to see you all again, and this is the Year 11 Methods Thursday class. Again, this is based on the handout that I've given out in Connect or in classes for those who are attending classes. And I'm going to be I'm going to be going through question 8 from last lesson, as well as looking at the notes for this lesson as well. And we're going to move through it and see how we go. So let's get started. So in question 8 yesterday, we were trying to sketch up some graphs based on based on their equations. And fortunately, the equations were given to us in a pretty easy to interpret form. This is our x-intercept form, so it was really easy to tell where they cut through the x-axis. And by substituting x equals 0 for all of them, we could really easily work out where the y-intercept was as well. So I'm going to be doing 4 of these. I'm not going to do all 6 rather. I'm just going to do these 4. Just to demonstrate sort of roughly what we're looking at for doing these ones. Now, what we're actually wanting to be able to do is produce sketches. So the entire point of these is to produce sketches. Sketches do not have to be perfect, but they do have to cover the key points on the graph. In this particular case, we are covering the coordinates of any points where the function cuts or perhaps just touches the axes. And we're going to be looking at the behavior of the function as x gets large, positively and negatively. Now, this has a particular meaning in math, or a particular way that it's written out in mathematics. What we say is as x tends to infinity, y does something. It might tend to infinity or negative infinity. It might even tend to 0 or something like that. But we usually say as x tends to infinity, y tends to something. Or as x tends to negative infinity, y tends to something as well. So that's what we're generally saying, the behavior of the function as x gets large positively and negatively. Now we saw our cubics yesterday, they could end up being like that. And in this situation, as x gets large negatively, or so as we go further in to the left, y gets very large negative. So we would say as, well, for this particular one, as x tends to negative infinity, y tends to negative infinity. Note that we're not saying x equals infinity. To say something is equal to infinity doesn't actually mean anything in mathematics. Infinity is not exactly a number. So we just say it goes towards infinity or tends to infinity. The other way that it could be drawn is we could have one that looks like that, where as x goes to the left, y actually goes up. So that would be as x tends to negative infinity, y tends to infinity. And conversely, we would make similar statements. So as x tends to infinity for our one here, y tends to infinity as well. But we'll have a look at those. We don't need to use these kinds of formal mathematical statements just yet, but it'll be good to get used to them for when we talk about it in the future. So let's have a look at our first one here. I'm going to match the colors to the highlighting that I've done. So I'm going to use my orange pen for this one. So here we've got y equals x plus 2, x take 2, x take 5. So this is in in x-intercept form, so it's pretty easy to see. In order for this to be 0 inside these brackets, x is going to need to be negative 2. So it'll pass through that spot. X is also going to need to be 2 for that second bit to be 0. And for the third bit to be 0, x is going to need to pass through 5. So what's the y-intercept going to be? So the y-intercept occurs when x is equal to 0. So that's just going to be, if x is 0 in all these cases, we end up with 2 times negative 2 times negative 5. That's 2 times 2 is 4, times 5 is 20, and we've got 2 negatives in there, so it ends up being positive, so we're up there. So I can sketch my, my line there. There we go. This may not be completely perfect. Let's try that again so it actually goes through my 3 points. Doesn't need to be perfect, I just need to make it clear which points I'm actually expecting to move through. And in fact, this isn't necessarily going to be a turning point up here. I've marked it as a turning point, but we don't know whether it's a turning point or not. And in fact, it's actually quite unlikely that it would be a turning point. So that's that one there. We've got our second one here. Also, we're having a look as this tends to as x gets very large, we expect y to get very large as well. As x gets very large negatively, we expect y to get very large negatively there too. So I'll have a look at this next one. What happens, or how do we get y, or how do we get our x-axis intercepts? This is one of our cases where the whole thing's going to be 0 if x is equal to 0, so that's one of them. The whole thing, if x is 3, then we've got another intercept there. And if x is 7, we've got another one there. Our y-intercept in this case has already been given to us. If x is equal to 0, y is also going to be 0. And we need to work out what's going to happen as x gets large positively and negatively. Now this one's a bit hard to work out. What we've actually got to look at is what's going to happen to the x cubed term. Is x cubed, because x cubed is going to be our dominant term in the polynomial, and what we can do to work that out, we could have worked that out by multiplying together all of our x terms, because that would be the only one that ends up being an x cubed terms. X times x times x is x cubed, so that means that as we expect x to get very large, we would expect y to get large. Positively. As x gets large negatively, then we would expect y to get large negatively as well. But what happens here? We've got x times negative x, remember to include that negative, times x. X times negative x times x is actually negative x cubed. So we expect this to do the opposite. We expect it to go very far down like that. And we would pass through these 3 points. It doesn't matter if my sketch is a bit dodgy, because the main thing is that we're roughly going through those 3 points. Now it gets a bit hard for me to draw that accurately on this touchpad sometimes, but we get the idea. And in fact, I'm going to correct that so it doesn't look completely awful. Let's draw a few at a time, go down like that. We've got that one going up like that, and then that going off like that. So that's roughly what we expected to do. Sketches don't need to be perfect. But over here, I've just done a few little sketches of those. I'll actually clear that. So I'll type this in. And it's good to use the actual proper variable notation there. Otherwise, ClassPad can get confused. So we got x plus 2, x take 2, x take 5. That's that one there. And I know that my axes are going to be quite large, or my y-axis needs to be quite large. So I'm going to go from negative 20 to 20 just to get a good range on that. And I can click and drag on that, bring that in, and that's what we get. So that looks about right, fairly similar to my graph on the left. My second one is y equals, let's do our proper things, y equals x, then 3 take x, and then x take 7. There we go, let's sketch that one up. And there we go there. Let's draw them on top of each other. There we go. So our second one, now we've got the colors a bit different, but it's doing roughly what I expected it to do. It's going down, then up again, then down again. Now I haven't got the turning points correct. We don't need to for what we're doing here. We're just looking at doing the x and y intercepts. So So we got those two there, and those look good based on what we expect. Let's have a look at this one. We've got x take 1, so x is going to need to be 1 for that one. We've got x take 3, x is going to be 3. What do we expect it to do? We expect it to get very large in this direction, or we expect it to get very large, or y to get very large as x gets very large, and we expect for y to get very negative, large negatively, as x goes negative. Let's get that line sort of there. So we expect it to do something like that. But what is this going to look like? Oh, and first up, otherwise, what is the x-intercept? Oh, sorry, what's the y-intercept going to be? If x is 0, we've got -1 times -3 squared. So that's actually going to end up being -9 because we've got 3 negatives in there. It'll be a negative like that. So we expect that to look, and drawing this can be a bit of a challenge sometimes on the touchpad, but there we go. Now we've got something a bit special. We've got a squared symbol there. Now what that means in terms of sketching is that that is going to be a turning point. So normally we don't know exactly where a turning point is going to be, but I would expect that to be a turning point there. So that's roughly what I'd expect. No, let's see if I can do that again. So we would roughly expect that to look like that. And that's just a feature of when we do that squared. Normally, basically it means we've kind of crammed 2 of our x-intercepts into one spot, and the only way that works is if it ends up being a turning point. So let's sketch that up here, just so we know what it looks like. And that is x take 1, x take 3, all squared, and see if I've done the right thing. Yeah, that looks good. It looks like I've got my my y-intercept of -9, and we've got 1 and 3. My turning point is a bit off center, but it doesn't really matter. We're not really worrying too much about the turning point for these particular ones, but I have got it going off in the right directions. So this last one is a bit different as well. We've got x minus 2 all cubed, and what that means is that this is actually going to cram 3 of my turning points into one spot. And this is actually going to look like my regular parabola. We don't need it to be perfect. Also, what's going to happen for my y-intercept, if x is equal to 0, we've got -2 to the power of 3, which is -8. So it's going to pass through -8. But because we're cramming 3 turning points into the one spot, it's actually going to do it's going to go up like this, and then it's going to go horizontal, and then it's going to start getting very large again. So that's a sketch of roughly what we'd expect that to look. So let's have a look at that. That's going to be x take 2 all to the power of 3. We sketch that, and yeah, that's what it ends up looking like. It doesn't have any of the, it doesn't have 2 turning points like these other sketches end up having if I sketch them all on the same thing. It doesn't have 2 turning points because it's actually crammed all its, or both of its turning points into the same spot in a funny sort of way, and all of its 3 x-intercepts into the same spot. But yeah, those are all 4 of our sketches all done up separately on the class pad there. So let's have a look at what we've got next. So we're going to have a look at a few different graphs, and the graphs we're having a look at is y equals the square root of x and y is 1 over x. Now we had a brief look at these, but we're going to have a look at them in more detail, and what we're going to do is we're going to consider y for particular values of x. So when x is, so we've got y equals square root of x. When x is equal to 0, what's y going to be? Square root of 0 is 0, so we expect that to just be 0 there. What's the square root of 1? The square root of 1 is 1. What's the square root of 2? The square root, the square root of 4. The square root of 4 is 2. What's the square root of 3? Again, the square root of 9 is 3. So I can just sketch that, and it's really good to practice doing your sketches. So in this sketch, I've got 0, 0 sort of pass through there. I've got 1, 1. I've got 4, 2. And I've got 9, 3. So it's always good when you don't have a set of axes, or in general actually, it's always good to actually label what your x and y coordinates are, so that when you're drawing your thing, even if it's not perfect, it can generally be understood that that's what you meant to draw. So I've labeled my points, that's a sketch of that one. What is this one? It's 1 over x. If x is 0.5, 1 divided by 0.5 is 2. When x is 1, 1 over 1 is 1. When x is 2, we've got a half, or 0.5. And when x is negative 1, what have we got? 1 over negative 1. Y is going to be negative 1 as well. And I can draw a sketch of that. And let's sketch those points. Now this one might be a bit counterintuitive. We have covered this one before. This is the reciprocal function. So we've got 0.5 and 2. We've got 1 and 1. We've got 2 and 0.5. So, and I'm going to write that. This is 1, 1. This is 0.5 and 2. And then we've got negative 1 and negative 1, which is down there. Now, you may not remember exactly what this one looks like, but I'll do it here. This is y equals 1 divided by x. I'll just do this one, put it back onto default. And I'll drag this one in. There we go. In fact, I'll just clear all again. Drag that back in. There we go. And that's what it looks like. Now, it is a bit unusual looking, but basically, this is the reciprocal function. So what we've got, as x gets very large, we expect it to get very close to 0, but never quite reach it. As x gets very large negatively, we expect it to, no, I'm going really rubbish at drawing these today. There we are, you get the idea. Usually we like to put little arrows on these as well. So as x gets very large positively, we expect y to go to 0. Same as x gets very large negatively, we expect y to go to 0. But as x gets close to 0, we expect y to get very high if it's coming from the positive side, or it get very low or very negative when we go up from the negative side. And this is our reciprocal function. Because 1 divided by 0, when x equals 0, that doesn't actually exist, but it does get very close to 0. So if we've got a very small number here, it will become a very large number. And if it's positive or negative, it will retain that positivity or negativity. So that's what we expect that one to look like. Then we've got slightly different graphs. What does this one look like? That is y equals the square root, just a second, oh, that's the wrong symbol. Y equals the square root of x minus 2 subtract 3. Note that the subtract 3 is outside that. Let's sketch that. What's it done there? It looks like, and I'll just put in my y equals the square root of x. So this is our standard function, y equals the square root of x, and this is my square root of x minus 2 minus 3. What's it done there? Well, it looks like the whole thing has just shifted to the right a bit and then shifted down to a bit. Otherwise, it looks like it's the exact same line, and it is in fact. So let's sketch that. And I'm just going to do a rough sketch. I'm not going to worry too much. about being completely accurate. So, but it starts at -2, 3. So where's it moved? It's moved 2 to the right, and it's moved 3 down. Does that make sense? It's moved 2 to the right and 3 down. There we are. So this has undergone what's called a transformation. It's just shifted a little bit. Otherwise, it's still similar to y equals the square root of x. It's just been shifted around a little bit. Its starting point has been shifted. Same for this one. Let's try sketching that one. First, I'll do my 1 over x. And then I'll do my, let's get a fraction in there. Ooh. That's going to be 1 over x take 2 take 3. Now, if I don't do my y equals, it will assume that it's going to have a y equals in there. So that was my original function. And this one, what will happen to this one? And again, and it's a bit hard to see, but what's happened is that the entire thing has shifted over by 2 and down by 3. So now instead of tending to 0, it's tending to -3. Instead of going infinitely positive and negative at 0, it's going infinitely positive and negative at 2 instead. So let's sketch this. And there's a special thing we tend to do in these situations is if we know that there is a what's called an asymptote, and I'll spell that in a second because the spelling's quite special. If we know there's going to be one of these things where it tends to infinity or it tends to a number without actually ever really getting there, and this is a special word called asymptote. It's got a silent P. Asymptote. So this is at 2. We mark these points. This is at -3. We mark them, and we often mark them on the axis. So that's going to be 2 and -3, but otherwise it looks the same. And there we go for this other one. I've got the colours mixed around a little bit. Now, one of the things was we would have noticed this went through 1 and 1 up here, and it went through -1, -1 down here. So this one's going to go through, crossed by 1, it's going to go through 3, -2. That's one of the points it's going to go through, and we can see that there. It's going through 3, -2 up there. And it's going to go through 1, -4 as well, which is that point there. And we can see that on our one up here, goes through 1, -4 there as well. And its one, again, has been moved 2 to the right. And it's been moved 3 down. Now, in fact, for any function, if I was to do the f of x subtract a and then add b onto the end of it, it would be moved a units to the right, and it would be moved b units up. Note that there is a subtraction in here. This is a bit counterintuitive. By subtracting something, we are moving it to the right. By adding it, we will be moving it to the left, which is the negative direction. But when we add our number, we move it up, which is the positive direction, and when we subtract it, we move it down, which is the negative direction. It's a bit the opposite of what you may expect, just like when we were finding our x-intercepts up here, we actually had to take the negative x value to work out what the x-intercept actually needed to be. So it works like that in the same way. So yeah, so that's the basis for having a look, or that's a look at a few of these different kinds of graph, our square root function and our reciprocal function. And we should now be able to do exercise 7b. And we should be able to say, what is the equation of these other ones? So for this one, this being shifted right by 3, so this is the square root of x. So b is going to be y equals the square root of x take 3. It's been shifted to the right by 3. C is being shifted up by 4. So C is going to be y equals the square root of x plus 4 outside of our square root. And D, it's had a bit of both of them done. It's been shifted to the left by 3, so that's going to be the square root of x plus 3 now. It's been shifted down 5, so that's going to be subtract 5 in there. And that's a few examples of what we can do. And it's got a few examples here for our reciprocal as well, in the form y equals 1 on x plus c. So this is just being shifted up or down some. And then we've got ones that are being shifted left or right as well. So we can have a practice of those. And we want to be able to describe how they compare as well. Question 9 is quite a good one in here. I quite liked it. Oh wait, no, I'm thinking something a bit different. Anyway, so these are just explaining how all of these can be solved there. And yeah, we should be able to do that. Answers are in the back of the book. This is exercise 7b. So this is exercise 7b in the methods textbook. So you can have a look at that, and good luck.